I don't know if you can hear us, but can you unmute yourself, please?
Local Hilbert space. Although I learned from Anton that maybe the best way, and we should see there's a chat. That's why it just changed.
Yes. It should have been fixed. Sorry.
Okay. Yeah, so I wrote this Hilbert space, but probably a better description is to use this operator algebra framework. We're going to be interested in the limit that the system becomes of infinite size. And when we say gap phase, so that means that we have a Hamiltonian acting on this Hilbert space. It's a local Hamiltonian, it's a sum of local terms, and there's an energy gap. So if you look at the energy spectrum, there's a few, maybe some finite number of ground states, and then a finite gap to the excited states in the limit that the system size goes to infinity. And we know mainly from experience, there's not really a proof of this, that gapped phases can be described using topological quantum field theory and higher categories. So that's why we have to do all this math to really understand what's going on in these phases of matter. So what's going to be important for my talk is this distinction between a bosonic system and a fermionic system. In a bosonic system, your operators from every different site commute with each other. If you have a fermionic system, then that means that these local Hilbert spaces have a Z2 grading by fermion parity. So you have, for example, fermion operators, which satisfy some anti-commutation relation. And then there's always a fermion parity symmetry, which is just this total Z2 grading, which is just whether the total fermion number in your system is even or odd. So we're also interested in symmetry in this talk. So when I say symmetry, what I mean is there's some global symmetry group G. So we have operators that act on the Hilbert space, RG for each G, which commute with the Hamiltonian. And we're assuming that the ground state is invariant under this symmetry. Now we could relax this a little bit and have some projective phase and so on, but that's actually completely unimportant. So just assume for simplicity that it's one. So when I say fermionic symmetry, then we're interested in what we call a fermionic symmetry group, which I think in math is also called a supergroup. So there we have a bosonic symmetry group, which is this fermionic symmetry group modulo fermion parity. The fermionic symmetry group is some Z2 extension of the bosonic symmetry group. The bosonic symmetry group is the symmetry that acts on bosonic operators. Fermionic symmetry group is the symmetry that acts on the fermionic operators as well.
Excuse me, are you allowing the ground states to be more than one dimensional?
Yes.
So to clarify, the yesterday's was about uniquely gapped state.
No. I think Anton didn't assume invertibility. Did you?
What you might talk?
You didn't assume unique ground state.
Oh, sorry. No, actually, it did. An infinite volume that's somehow not a very. I'm talking about finite volume or doesn't.
An infinite volume. Well, that's what
infinite volume is asking. In infinite volume, it's very rare to have ground state degeneracy. There's no good.
No, you can have topological ground state degeneracy.
In infinite volume, all the distinct ground state on a torus, for example, become the same ground state. You cannot tell them apart. So
from using local operators, but there's non-local operators that
those non-local become ill-defined in infinite volume limits. And in infinite volume, it's extremely rare to have degeneracy.
That's
unstable.
I don't agree with that statement. I don't know why you say that. I mean, all these topologically ordered states have ground state degeneracies in the infinite volume.
I mean, just if you have translation variance, it doesn't have any anyons, it must be the same state.
If it doesn't have anyons, but if it does have anyons.
No, I'm saying it doesn't have actual insertions of anyons.
No. Z2 tor code infinite volume has a ground state degeneracy of 4.
No, all the states are actually the same state as far as local operators.
Yeah, but we want to consider as the non-local operators.
No, non-local, those don't survive in infinite volume limit. They're not legit operators in infinite volume limit.
Well, I mean, maybe you're taking the infinite volume limit in a way that I'm not comfortable with. I mean, well, okay, I think we should discuss this. That's an interesting point. I've never heard this.
fact is that your formulation is really the gap so the gap state condition is really selecting one-dimensional cubes.
Yes. No, but I think the difference is the following. So for me, state is something which just measures expectation values of our local operators in infinite volume. So,
but we need to generalize that because we need to confront this topological degeneracies as well.
all I'm saying is that these non-local ones in the infinite volume limit don't have expectation values. So there's not you cannot consider them as things which have.
Okay. I'd love to talk to you more about that, Abhina, to see why that's the case.
Is it that the degeneracy in infinite volume, the different vector become infinitely far apart, so to speak? So
Roughly speaking, yeah.
so you need to choose one theory.
But also to become indistinguishable with any local.
You know, I would probably say that that infinite volume limit is not very physically relevant. Because we care about these degeneracies and they're there, and in fact we want to exploit them in experiments and so on. So we want to use them actually. Okay, so
Unless the standard comment, this is not a supergroup.
oh, it's not? Oh, okay. I thought this was a supergroup. Okay, just delete that. Right. So this extension is classified by a 2 cocycle. And so that means that the symmetry operators compose in this way, twisted by this 2 cocycle. Okay. So once we specify the symmetry operators in the system, we've specified this 2 cocycle. There's no more like co-boundary ambiguity once we specify the symmetry operators. Okay. Right. So this symmetry has a bit of extra structure, some of which will be important, but most of which will not be for my talk. So there's also a Z2 grading, which tells you whether the symmetry is unitary or anti-unitary. And we're also interested sometimes in situations where the symmetry group has some action on space. So if you have a square lattice, for example, where you have translations and rotations and reflections. So there's another map that tells you how the symmetries act on the isometries of the space. So overall, if you want to characterize this fermionic symmetry, you really should specify this bosonic symmetry group, the 2 cocycle, this Z2 grading for unitary, anti-unitary, and then this alpha. But in my talk, I'm going to assume alpha is 0, and often I'll assume the S1 is 0 as well. Okay. So when we think about bosonic topological phases in 2+1D, and there's a belief, there's not a mathematical proof or anything, but there's a very strong belief that these are fully characterized by 2 quantities. One of them is a unitary modular fusion category, unitary modular tensor category. So you can think of this as a 3 category. And this object determines the algebraic properties of the quasi-particle excitations of this medium, which we call anyons. And this, then we have another quantity, the chiral central charge, which specifies the chiral central charge of the boundary theory. And this modular tensor category determines the chiral central charge modulo 8. Okay, so very quickly, maybe just establish a bit of notation. Unitary modular fusion category has a finite set of anion types, which are this isomorphism classes of simple objects in the category. We have these fusion rules, and then we have these vector spaces. So there's like a fusion space, that's this vector space VABC, and then there's this splitting space, there's a dual of that vector space. And then we have these F and R symbols, which tell you how you move between this diagram and that diagram. One thing that's quite important for what I'm going to be saying is that when we have these fusion and splitting spaces, then there are these basis transformations that we can do. And when so these basis transformations we view as gauge transformations in this theory. And when you apply these basis transformations or these gauge transformations, we call them vertex basis gauge transformations. Then they change the F and R symbols in this way. And so you have modular tensor categories with different, as long as the data that you specify, like the F and R symbols, are gauge equivalent to each other, then it's the same modular tensor category that you're talking about. Okay, so now I want to briefly review the case where you take this bosonic topological phase and you add symmetry. So this is what was we discussed almost 9 years ago now. So the first thing that you need to understand is these invertible maps, which are called braided autoequivalences, which map the category back to itself. They permute the anions in some way, which preserves all of the gauge invariant data, like the fusion rules, the quantum dimensions, topological twist, modular S matrix. And the F and R symbols transform but they stay the same up to gauge transformation. So basically we have this equation where the sim-equal means up to gauge transformation. So another key thing that's going to play a very important role in my talk is this idea of a natural isomorphism. That's when you, that's a particular kind of this braided autoequivalence, which acts in a very, very trivial way. It does not permute the anyons. And when it acts on elements of this fusion and splitting space, it just acts by a set of phase factors that decompose. Okay, so these are completely trivial operations. And so we generally want to consider equivalence classes up to these natural isomorphisms. And so if you consider these braided autoequivalence with this equivalence relation up to natural isomorphism, that forms a group, which is this group of braided autoequivalences. And you can also generalize this whole discussion to the case where the anti-unitary symmetry, so everything acts anti-linearly on the category. So if we have a global symmetry, the first thing we need to specify, okay, this is blocked out, we need to specify this thing which is written as bracket rho, which is the group homomorphism from the symmetry group into this OT-C. And so this object acts on the fusion and splitting spaces via this, I just written everything out kind of explicitly in terms of this U matrix. So this U matrix also plays a very important role for us. So that means that when you apply to the R and F symbols, you get back what you started with up to essentially this basis, this gauge transformation, which is this U symbol over here. And so you can always choose a particular, you can make a particular choice for U so that this particular combination is just one. Trivial. Okay, so once you specify this rho, that immediately defines an interesting third cohomology class. So this is a third cohomology class where the coefficients are in an abelian group, which is the abelian group formed by fusion of abelian anyons. Those are the objects which have quantum dimension 1. And this third cohomology class, I'm not going to tell you how to compute it here. It's a little bit involved, but there's an explicit formula that you can write down that computes this. You can think about it in two different ways, which are equivalent, of course. One way is that you can think of this as a kind of obstruction, and I'll tell you more about what this obstruction is. Or you can think about it as telling you that the theory actually has an interesting two-group symmetry. Okay, so the two group is composed of G, which is the zero form symmetry, and this group of abelian anyons, which is the one form symmetry. And then this O is part of the data that characterizes a two group. Because as probably everyone knows here, the two group requires a choice of 3 cocycle. Okay, now, if this obstruction vanishes, then we can define a consistent set of U1 phases, which this is what we call symmetry fractionalization. So it's for every anion A, we have a map that takes in 2 group elements and gives us a U1 phase factor. So diagrammatically, it's you can think about it like this. You have this 2 + 1 dimensional theory. We can have symmetry defects for G and H. So, and the point is that that junction between GH and GH is interesting. When you take an anion line and you pass it to the junction, you get a phase. Okay, so this phase these are what we call these eta symbols, and this is what we call symmetry fractionalization. So in condensed matter physics, there's many situations where we have particles which carry fractional quantum numbers of the symmetry group. Nobel Prizes have gone for this kind of thing. And this is the mathematical way that we describe that. It's using these kinds of moves in the corresponding top-left degree. Okay, and one interesting factor of the classification of such data is that inequivalent choices of this symmetry fractionalization data form a tensor over this second cohomology group. So basically, you need the third cohomology class to vanish to be able to consistently define this structure. And when it vanishes, this data forms a tensor in the second cohomology group.
So I would have thought that you would still have those scalars even if this obstruction didn't vanish, but that they wouldn't form a two cocycle.
We didn't go down that path because part of what we wanted to do, there's like a whole kind of mathematical setup that's behind this, which is what we have this quantum many-body system, and we have anyons, and we apply the symmetry operation. We want the symmetry operation to decompose as like unitaries that act locally where these anions are. And so for all that to be considered, we need the 3 co-cycle to vanish, and then we go from there. Now, I agree with you. It might be possible that you can define some kind of phase, but I'm not sure what their structure would be and how to think of it.
Is AU1 in this?
This A, little a?
No.
Or the big A?
Big A.
No, the big A is a finite abelian group, which is the abelian group formed by fusion of the abelian anions.
It's a mispo. So I should think of the abelian anion as perhaps living on that trivalent seam. And
Yeah, exactly. The way that you,
computed by the braiding with that.
yeah, so well, that's how you can go from one class to another. That's the structure. So if you start with one class, then you can get to the other class by imagining you twist this picture by having a abelian anion on the line on the junction, and then that gives you an extra phase. That gives you the torso. Okay, so then that brings us to the 2th anomaly. So once we choose this, once we have this choice of symmetry fractionalization, which is this, concretely it's in terms of this rho, u, and eta that I've defined. So mathematically, I think you could call this a categorical G action on the modular category. Then this data immediately defines what we call a 2th anomaly, which is an invertible G-symmetric topological phase or TQFT in 3+1 dimensions. So this is believed to be classified by this Bordism group. So Bordisms of 4-dimensional manifolds with maps to BG. Now, in general, it's actually hard to find a formula that tells you exactly what the anomaly is that you can easily calculate. There's a very simple formula if you're interested in the relative anomaly. So if you consider 2 different symmetry fractionalization classes, and you want to understand what is the relative anomaly between those 2, there's a very simple formula that you can write down. However, if you're interested in the absolute anomaly, like given this data, what is the anomaly? That's a much more involved thing. So basically what you have to do is you need to take this algebraic data and you need to input it into a state sum construction for a 3+1D state sum for invertible G-symmetric TQFT. And so a few years ago, we wrote a paper where we just kind of explicitly wrote out exactly what the state sum looks like and how you do this calculation. Now, if G is unitary, then this you can think about this obstruction, or sorry, this anomaly as an obstruction to extending this modular category with a categorical G action to a G cross braided tensor category. In that case, the obstruction is valued in this 4th cohomology group. Okay, so it just so happens that when G is unitary, that Bordism class is fully captured by the cohomology class. Okay, so now we come to fermionic topological order, which is the main subject I want to talk about. So if we talk about gapped fermionic phases in 2+1D, again, we believe that we understand how those are fully characterized. And in this case, we believe that what you need is a unitary supermodular fusion category. And this supermodular category determines the chiral central charge modulo 1/2. And so you can think about the simple objects in this supermodular category. They decompose as a set. They decompose as your anions times the identity and psi, which is a fermion. So this fermion we think of as a local fermion. So the whole reason why we can't consider modular categories anymore, we need to consider supermodular categories, is because physically the system has this local fermion, which needs to braid trivially with all the topological excitations. And so we don't get a modular category anymore, we just get the supermodular category where the fermion, the braiding of the fermion with every other object is trivial. So the fermion is an invisible object in this theory. And because the fermion is an invisible object in this theory, the modular S matrix decomposes in this way. And this MA psi is just mutual braiding between any anion A and this fermion. If you have an abelian subcategory, then this abelian subcategory decomposes as a product of the local fermion and then everything else. Okay, this is true for any abelian subcategory. Okay, so another thing that's going to play an important role for us is this notion of a minimal modular extension. So given any supermodular category, you can take a minimal modular extension to get a modular category, and there's exactly 16 different ways of doing this. The 16 different ways give you a modular category where the central charges differ by half integers. And so once you get to chiral charge differing by 8, you're back to where you started again. So they're indexed by this integer nu. Now this modular extension, which I'm always going to denote the modular extension by this like check on top of the C. This is what's called a spin modular category. So the interesting thing about a spin modular category is it's just a modular category, but it has a special object, the fermion, which induces a Z2 grading on the modular category, where you have one piece, which is just the original theory, the original supermodular theory, and you have another piece where everything in that piece grades with the fermion with a -1 factor. So physically, we think of these as defects of this fermion parity symmetry, or like fermion parity vortices, where when the fermion goes around it, it gets a minus.
That would also be defects in the spin structure.
Yes, yes. And now this fermion parity, the defect sector itself actually decomposes as well into 2 sectors, where the V-type fermion parity defects have the property that when you fuse with the fermion, you don't get the anion back. Whereas the sigma type defects, when you fuse with the fermion, you get the same object back. Okay, so there's another object that's going to be important for what we're going to do, which is when we think about the fusion ring of this supermodular category, and we look at the characters of this fusion ring, which are just U1 phases. So specifically what I mean is, suppose that let K of C be an abelian group, and this is a group which consists of a set of U1 phases for every anion A, which respect the fusion rules. So you have this formula, zeta A times zeta B, zeta C, if A and B uses C. Okay. So note that this immediately implies that zeta psi has to be plus or minus 1 because the fermion squares to the identity. And then we're going to let K plus of C be the subgroup of K where zeta psi is plus 1. Okay. So this already, there's already something interesting here, which is there's some situations where this subgroup is actually the full group. And then there's other situations where it's not the full group, there's an extra Z2 factor lying around. So if there's a choice where the zeta psi can be -1, then obviously this is not the full group. So if you mod out by this K plus, then there's an extra Z2 lying around. And otherwise, if there's no such choice, then obviously K plus is the full K. Okay, so this is some supermodular categories have this situation and some of them have this situation. And this is a very important distinction between supermodular categories. Now, it turns out that if you have a minimal modular extension, C check, which contains a fermion parity defect V, and that V is abelian, then it turns out that you can have this zeta psi be -1 because you just set zeta psi to be the braiding of all the anions with that abelian fermion parity defect, and you will get -1 for this factor. So in this particular situation, you get indeed this case where K of C is larger than K plus by the Z2 factor. And in fact, the reverse statement is also true. So this is an if and only if statement. So this is the case if and only if a modular extension of C contains an abelian fermion parity defect. Okay, so now we'll soon come to why I told you this. So in the bosonic case, recall that we had a group homomorphism from G into this aught C. And in particular, we had these maps rho, gave us this U factor. Then we had these natural isomorphisms, which decomposed as these phases. So one of the first key thing that we can derive, I don't have time to explain how we derive this stuff, but this is kind of the result. One of the things that we can derive is, okay, let me back up. The reason this whole thing is interesting is because fermions, if you have a fermionic phase, on the one hand, the fermion is local. On the other hand, there's something non-local about it still. Okay, you have a local fermion operator, but fermions at far different points anti-commute with each other. So this is why we kind of need to confront this locality of the fermion in a fundamental way. And one of the things that you can derive is because of this locality of the fermion, you can derive that this particular U has to be 1. This is a pretty non-trivial condition. So anyway, this has to be the case. And now this doesn't do that much for us. It does one important thing, which is Of course, every element of OT, there's always a representative where this UG can be set to 1. If you don't believe me, that's just because if it's not 1, then you can just modify this U using a natural isomorphism by setting gamma psi to just be the square root. Maybe the negative square, it should be probably negative 1/2. And then you can cancel out instead of 1. But the important thing that, so the conclusion of this is that even you don't cut down OT at all by making this requirement. So the set of autoequivalences which satisfy this requirement, modulo natural isomorphisms, is still OT. But what this does for you is that because you now require this to be 1, any remaining natural isomorphism that you need to consider must satisfy gamma psi as plus or minus 1. Okay. So this is one key point, which is once we have this condition, which I didn't tell you how to derive, I just asserted it, but we can derive it, that what's left over for these natural isomorphisms is that gamma psi should be plus or minus 1. Okay, but now that means that when we talk about these autoequivalences, that we have to actually be a bit more refined, because there's another requirement that we can derive, which again, I don't have time to derive for you, which is that because the fermion is local, we also need to require that gamma psi is always plus 1 when we consider this structure. And so that means that if we only mod out these autoequivalences by natural isomorphisms that satisfy gamma psi is 1, we actually get a different group than that OT. We get a group that we call the group of locality respecting automorphisms. That's what we call as LR of C. Now, so LR of C may or may not be a different group than OT. So in some case, depending on some details of the supermodular category, it could be the case that this LR is the same as OT, or it could be the case that, again, there's an extra Z2 factor lying around. So LR might be like twice as big as OT. I lost everyone, or everyone's good. Okay. Yeah.
If you need this condition, why are you interested in the full OT compared to LR?
Well, OT is always there, so it's useful and interesting to consider the relationship to OT, but we will mainly be working with LR.
LR just the automorphisms of the minimal measure extension.
Yeah. That's a different group. Because you could have automorphisms of the modular extension, which actually act trivially on the supermodular part and non-trivially on the extended part. Okay, so to tell you more about the distinction between LR and OT, as I said, sometimes they're the same and sometimes this one's twice as big as that one. And to understand the distinction, what we can do is we're going to define a special natural isomorphism that we call upsilon psi. And upsilon psi has the property that these phases are 1 for every anion if that anion is not psi, and it's -1 for the psi. Okay, so it's just this very simple natural isomorphism. But actually note that when we talk about natural isomorphisms, there could be an ambiguity when we decompose this action in terms of individual phase factors. Because if I have gamma A, gamma B, gamma C, that might be equal to gamma prime, this combination, if gamma prime and gamma differ by one of these U1 characters of the fusion ring. Okay, so if they differ by a U1 phase that obeys the fusion rules, then these are going to give me the same natural isomorphism. So if we can represent upsilon psi with a gamma prime psi, which is +1, at the cost of making the other gamma primes not 1, then we're going to say upsilon psi is locality preserving, because there's a choice of this decomposition where locality of the fermion is preserved. So when does this happen? This happens exactly when there's a choice of these phases for which zeta psi is -1, which was exactly the situation where K of C was twice as big as K plus of C. So if this is the case, then this upsilon psi is locality preserving. Otherwise, if this is not the case, then obviously I cannot I cannot convert this decomposition where gamma psi is -1 into a different one where gamma psi is +1. And so now we're stuck with gamma psi being -1. And I told you that that violates locality because locality of the fermion requires gamma psi +1. And so then we conclude that this upsilon psi is actually locality violating. And that's exactly the situation where there are no such phases, zeta psi being -1. That's the situation where this K plus.
Excuse me. Yes. Did I get it correctly that your natural isomorphism is monoidal? And is it obvious that the one you are giving is monoidal?
I don't know quite what that means.
Monoidal means compatible with the tensor product. And in particular with the fusion rules, but it's stronger than this.
I think it is, but I'm not sure I can produce a proof of that. Actually, this is, I think, an interesting broader point, which is that, this is what we derived when we were trying to understand symmetry fractionalization in a quantum many-body system, that you have these space factors. And in the category theory literature, when people talk about natural isomorphisms, we assume that it must be exactly this that they're talking about, because we derive this from these considerations of a quantum many-body system. So I think this satisfies all the appropriate requirements, but actually I'm not entirely sure myself.
No, but it can't. Seems like it can't be monoidal because take A to be 1 in the top formula.
Right, take
that counterexample doesn't seem to work, but I doubt it's monoidal. Okay. We'll discuss this later.
Yeah, I would be happy to know more about that. Okay, so if this upsilon psi is locality preserving, then it doesn't matter if we mod out only by locality respecting isomorphisms or the full natural isomorphisms. So these two groups are the same. On the other hand, if this upsilon psi is locality violating, then this OT C is, OT LR is twice as big as OT C. Okay. So an example of this particular situation where this upsilon psi is locality violating, this is very rare. It's hard to find these examples. This is the more generic situation. But an example of this is what people call SO3 level 3. That's a supermodular category, which corresponds to the integer spin sector of the SU2 level 6 theory. So this is actually always an interesting theory to look at for interesting properties. Okay, so just to summarize what I said, upsilon psi is locality preserving. That's equivalent to OT LR, is the same as OT, which is equivalent to this C mod K plus being Z2, which is again equivalent to some minimal modular extension. C check has an abelian fermion parity vortex. If upsilon psi is locality violating, then OT C is half as big as OT LR, whereas these characters, abelian characters, are. Okay, so then to define the symmetry action on the category, we need to specify a map from GB into OT LR, similar to the bosonic case. And these maps compose up to natural isomorphism. But again, this natural isomorphism may be either locality preserving or maybe locality violating. So this, so if we look at only equivalence classes with respect to locality preserving natural isomorphisms, then it's possible that this kappa will be non-trivial. So depending on whether OT LR is the same as OT or not, we either will have some kind of projective homomorphism where it's projective up to the center of OT LR, which is just this upsilon psi isomorphism, or rho, if this thing is always trivial, then rho will just be the regular group homomorphism. So the key point here is that it's possible to have some slight twist on rho being a true group homomorphism because there's a possibility of this projective factor. Okay, so then when we come to symmetry fractionalization, there's one more requirement that we need to specify, which again, I'm not going to derive for you, but we can kind of derive it from these considerations of a quantum many-body system, which is that, remember, we had this 2 co-cycle, which told us how GB gets extended by fermion parity to give us GF. So we have a requirement that these eta symbols, which define symmetry fractionalization, should be equal to this 2 cocycle that we get omega-2. Okay, so when I take the fermion through this junction, I should get exactly the same phase as specified by this -1 plus or -1 factor given by omega-2. And basically the physical reason for this is, if Rg times Rh, the G action times the H action is the GH action up to potentially fermion parity. What that means is that if I have a G defect and an H defect coming together at a junction, then there's a possibility that this junction has a fermion parity defect associated with it. And that is determined by omega-2. And when I slide the fermion through the junction, whether I get a plus or -1 is determined by omega-2. So that's basically the origin of this constraint. So now remember that in the bosonic case, when this rho was specified, we had this H3 obstruction, which also was, you can interpret as the theory had a non-trivial 2 group. So here we have even more obstructions. So first of all, we still have the bosonic obstruction. The bosonic obstruction now, though, is not valued in GB, comma A. It's valued in GB, comma this K, which remember was the abelian group of the U1 characters of the fusion ring. So we get this bosonic obstruction, and the meaning of this is this obstructs the possibility of any symmetry fractionalization class to be consistently defined on C. So this is kind of analogous to the bosonic case that I had mentioned way earlier, except the coefficients have changed slightly. The fermionic obstruction, we have a new obstruction, which we call the fermionic obstruction. And this takes values in 2 possible different groups, depending on whether this upsilon psi is locality preserving or locality violating. If upsilon psi is locality preserving, then this additional obstruction takes values in this group. Whereas if upsilon psi is locality violating, this obstruction takes values in this group. And basically the meaning of this obstruction is you don't want just any symmetry fractionalization class. You want a particular symmetry fractionalization class which satisfies this requirement. Okay, so if the bosonic obstruction vanishes, that means that there's some choice of symmetry fractionalization class, but it might not satisfy this eta psi being omega-2. So the second fermionic obstruction is the obstruction to finding a particular symmetry fractionalization class that satisfies this extra condition. Okay, so you have these 2 different obstructions in this case. So now once all these obstructions vanish, then basically we can define this fermionic symmetry fractionalization. So we have this sort of projective homomorphism from GB into this off LR, and then symmetry fractionalization is this group of phases. And then the main constraints that we need to remember then are that this U has to be 1, and this eta psi has to be omega-2. And then finally, you can try to classify the different patterns of symmetry fractionalization that are consistent with all this stuff. And this forms a torsor over H2, except now the coefficients are in the abelian anyons of the supermodular category modulo the local fermion. So I can't derive that either, but that's a result that you can derive. Okay, so that's the story for fermionic symmetry fractionalization. And so the next thing I want to do is I want to move on and describe anomalies of these fermion symmetry fractionalization patterns. So maybe before I do that, I'll just pause and see if anyone has any questions so far.
I was trying to work out how what you're discussing is related to this notion of G-crossed braided modular category. G-cross braided categories.
Well, so G-cross braided categories is kind of what I had mentioned earlier on in the bosonic case. So if you have a bosonic theory where you start with a modular category and then you want to add symmetry, then you pass through a bunch of obstructions, but at the end of the day, if they all vanish, you can define a G-cross braided tensor category. Here, what we're doing is we're starting with a supermodular category. We're trying to extend by a fermionic symmetry group. And then we have all these extra conditions along the way. So in a way, this is kind of a parallel of that story, but in the case where you have all these fermions lying around. So like all this extra structure that we're telling in the last 20 minutes, That's kind of how that original story gets modified when you have fermions.
There's also a notion of super G-crossed braided.
And that's what this is. Yes.
Well, we haven't yet gotten to anything G-crossed yet, because to get to G-crossed, we need to introduce symmetry defects and make sure that they can braid and fuse consistently. So I haven't yet gotten to anything like that. So far, I'm kind of just defining this fermionic G action on the original supermodular category.
Yes, my reason for asking is in the G-cross case and also in like G-graded extensions, you can, those obstructions that you're writing about, you can sort of understand as like homotopy classes of maps from the group G to some classifying space. Is there a description like that for what you're doing?
Probably, but I'm not very, I haven't seen it develop. Okay, so now I want to discuss anomalies in the remainder of time. Okay, so sorry, I already did this. Okay, so once a symmetry fractionalization pattern is specified, then this should define, what we usually call a 't Hooft anomaly in physics for this fermionic symmetry GF. And you've heard many times that the 't Hooft anomaly should take values in invertible TQFTs 1 dimension higher. So in this case, it should take values in 3+1D invertible GF symmetric topological phases or TQFTs. And this is classified by this fourth Bordism group with maps to BGB, but equipped with a kind of spin structure. This spin structure is an interesting twisted spin structure. It's not like a usual spin structure. So I'm not going to get into exactly what that means. Now we can actually calculate this anomaly exactly by, again, feeding all this algebraic data into a 3+1D state sum. And then that state sum will be a state sum for a GF symmetric invertible fermionic topological phase. So we kind of spelled out exactly how to do that in a recent paper. But there's another thing that we can do, which is we can try to understand how this structure arises by tracing additional obstructions that appear. So remember, in the original G-cross braided tensor category story, we had this H4 obstruction to defining a G-cross braided tensor category. So in the fermionic case, we're going to go through a bunch of obstructions until we can kind of define a certain kind of G-crossed braided tensor category. Now, in the case where the symmetry is unitary, this anomaly can be interpreted as an obstruction to gauging the fermion parity symmetry. And that's equivalent to an obstruction to extending the theory to a GB cross braided tensor category over the minimal modular extension. Okay? So basically what we're going to do actually to understand this obstruction more clearly is we're going to try to systematically get to a GB cross braided tensor category over the minimal modular extension. So first we're going to define a modular extension, try to extend these maps to aught LR to the modular extension. We're going to try to make sure they satisfy the appropriate group multiplication law. And we're going to try to extend symmetry fractionalization. And so there's all these layers that appear in trying to do this. And that's why you have various sequences of obstructions. Now, of course, I told you that these invertible fermionic phases in 3+1 dimensions are supposedly classified by this Bordism group. This is a very, very complicated group, and it's really hard to actually do anything with this. If you're an expert in various certain kinds of homotopy calculations, you can try to calculate this group for specific choices of GB, but in general, it's very hard, in my opinion, to work with this. There was an interesting work a few years ago which actually showed how you can decompose these invertible phases just in terms of a very concrete set of data. So there's a set of data, N1, N2, N3, and nu4. N1 is a one cocycle with maps from GB into the integers. Here, the subscript T just means that if GB is anti-unitary, it acts on these coefficients by an inversion. This is 2 cochains valued in Z2. This is 3 cochains. This is 4 cochains with U1 coefficients. So you need to specify this data. The data satisfies a series of consistency equations, which was derived in that paper. And this is how the consistency equations look. And in addition, there's various equivalence relations on this data, which were also to some extent derived. And one interesting aspect of this data is that when you look at the equivalences, this first piece of data is just lives in the first cohomology class. If the first piece is 0, then the second piece lives in the second cohomology class because this dn2 winds up being 0. But it's actually some some smaller piece of the 2 cocycle. We have to mod out by some subgroup of H2. And then similarly for the other layers. If N2 is 0, then this N3 lives in the third cohomology class modulo some subgroup, and then similarly for nu 4. Okay. Now, this data with these equations, interestingly, they have been matched to this 4 cobordism in the case where omega 2 is 0, but not in the case where omega 2 is non-zero. So I think that if we want the whole story to be complete, someone should show that this group is the same as this data when omega 2 is non-zero. I think that hasn't been done yet. Now, if these lower levels are non-zero, like if N1 is non-zero, then N2 no longer takes values in this group, but it's a torsor over this group. And similarly, if N1 and N2 are both non-zero, then N3 will be a torsor over this group, and so on. Yes.
Something about the previous, the last one. Yeah. So the anomalies all vanish, and if you're then gauging the fermionic symmetry,
They would need to vanish if we want to define this kind of extension. Yeah.
then looking at the gauge theory and forgetting about the GB cross structure of that, is that a way to find the minimum model extension algorithmically?
Like the obstruction-free one?
Yeah, obstruction-free case.
Yeah, we have a way of doing that. Yeah, we
Also,
can do that.
the obstruction doesn't vanish. I thought like supermodel categories always admit minimum model extension. So how do we see that?
No. So supermodular categories always admit a modular extension. The question is now we have this fermionic group that acts on the supermodular category, and we also want to extend the action of that.
Okay.
And then we want to define like symmetry defects and consider a whole G-crossed extension of the minimal modular extension. And so doing that may run into obstructions. Yeah, so another way of phrasing that is Z2 fermion parity by itself does not have an anomaly. That's why there's always a minimal modular extension, but a generic GF does have anomalies, which is why you run into obstructions.
Can I ask you another question? So I guess, sorry, the last slide. So I guess this data is what arises from the spectral sequence description of the Bordes group?
Yeah, it should be, but that's not how it was calculated.
Okay. And I was wondering, does this capture also just the torsion part of the Bordes group? Or because there should be some Z factor as well in degree 4, right?
Okay, yeah, so that's an interesting point. So for invertible GF symmetric phases, maybe I should have been more careful. The anomaly is really the torsion part of this. Well, what we call the anomaly is the torsion part of this. So this is the torsion part.
Okay.
Yeah. Thank you. I should have said. Okay, so the question is that how can we see the appearance of this data and all the equations and so on from the anomaly structure from the symmetry fractionalization data of the supermodular category? And the answer is we can do part of it, but we haven't succeeded in doing everything. So I can tell you how much of it that we can do. And so this is what leads to what I call the anomaly cascade, because there's kind of a sequence of N1, N2, N3, nu 4 of anomalies that appear of various layers. So that's why I call it anomaly cascade. Okay, so to understand what's going on here, I'm going to define C nu check. This is the minimal modular extension of C labeled by an integer nu. Okay, so remember that this integer nu specifies the chiral central charge modulo 8, whereas C by itself only specifies it modulo half. Okay, so the first layer of this anomaly cascade is that we have these maps from GB into aught LR of C, and we want to extend them to maps into aught LR of the minimal modular extension. Okay, but this may not always be possible. If it's not possible, there is a weaker lift that might be possible, which is that we map one minimal modular extension to a different minimal modular extension. Okay. So we have a conjecture. I wish we could prove this. If there's a mathematician here who has an idea, please let me know. Basically, we conjecture that this weaker lift is always possible. meaning that given a supermodular category C with this action, there always exists at least one pair nu1 and nu2 such that there exists this map rho check from C nu1 check to C nu2 check, and such that rho G check restricts to rho G acting on C. Okay. So yeah, we think this is true. We don't know, but assuming this conjecture is true, then it's almost trivial to just prove that if rho G is a unitary map, then any pair that satisfies this equation, nu1, nu2, must have nu1 actually equal to nu2. And okay, so this is the conjecture that I just wrote. I'm just repeating it on this slide. So then assuming this, there's a second thing that you can prove, which is that suppose this rho is now an anti-unitary map, then you can prove that nu1 and nu2 has to satisfy that nu2, C, the chiral central charge for nu2 is minus the chiral central charge of nu1, but that's equal to C nu1 plus some integer over 2. So O1 of G is this integer valued one cochain, basically. Okay. And then the other interesting thing is that if there's multiple such pairs, then this integer valued cochain is actually independent of which pair you're talking about, modulo 2. So it's also simple to prove this. So a corollary of this theorem is that if we have this collection of maps for each G, then this collection of maps is going to define this first cohomology class, which is exactly that first layer of the obstruction, which is that first layer of the anomaly that we found. So and again, we can't prove this, but we're quite sure it must be true that we conjecture that this O1 is exactly the obstruction to finding this lift. So this conjecture is that if we're given this, this lift, these maps define an O1, and there exists a minimal modular extension with these lifts for every G, if and only if this cohomology class vanishes. Okay, so this is an outstanding question. We don't want to prove this. That this is basically, there's a story for the first layer of the obstruction. And now suppose that this first layer of the obstruction vanishes. Now we can define these maps for the modular extension. But we want these maps to satisfy a certain structure for group multiplication. We want them to be this projective homomorphism. So this kappa check is the extension of what I had as kappa before, now to the minimal modular extension. So we know that kappa check should be trivial in OT, but it might be non-trivial in OT LR. So if we just assume for simplicity that we can forget about this distinction, we'll say that this upsilons are locality preserving, so I don't have to worry about this. Then basically what this says is that I want the lift to also be a group homomorphism, just as the original map on the supermodular category was a group homomorphism. So I want this to be the case, but I might have an obstruction to doing this. The second layer of the anomaly is an obstruction to getting this to be a group homomorphism. So to understand this obstruction, we're going to define this restriction map where it restricts OT LR on the modular extension to just the original OT LR. And we're going to define O2 to be what's left over after doing this sequence of maps for the extension. And so O2 has to live in the kernel of this map R, because on the supermodular category, this was a fine group homomorphism. The problem is when we extend it, when we restrict back to the supermodular category, it should be a group homomorphism, meaning that it should be, this map should be in the kernel. Go ahead and prove associativity of this 2 cocycle of this O2, which implies that it should be a 2 cocycle. And then you can modify each map by elements of the kernel. That gives a co-boundary ambiguity. So ultimately, you arrive at this obstruction. So O2 is the obstruction to lifting rho to group homomorphism, at least assuming this OT is the same as OT LR. There's a slight generalization of this whole story that you need if OT LR is not the same as OT, so I won't go through that. Okay, so to further understand what this obstruction is, and to try to map it to what we know about invertible phases in one dimension higher, we actually need to understand what this group is, this kernel of R. And unfortunately, we don't fully understand this kernel R. The first thing is we can show that there's always a Z2 subgroup in it. And that Z2 subgroup is generated by a map that we call alpha psi, which is the unique braided autoequivalence that just fuses a fermion to the fermion parity defects. So this is the unique autoequivalence that keeps all of the anyons in the supermodular category invariant, but it fuses the ones in the fermion parity defect sector by a fermion. Okay, so this subgroup is always in this kernel. You can see if we restrict to the supermodular case, it just acts trivially, so it makes sense. Now we have another conjecture, which is that in all cases, this kernel R is actually equal to Z2. We can prove this in various special cases, but we don't have a general proof of that. But we do, this is required if we want anomaly matching. If we want the O2 anomaly to match the classification of invertible fermionic TQFTs, we do want this group to be the same as that group. So it'd be very, very surprising if it was not the case by anomaly matching, but it would be nice to prove it just within the supermodular categories. Let me probably just do a couple more slides and then finish. Now, if N1 is, remember, let's go back to the characterization of invertible phases in 3+1 dimension. I told you that it's classified by this data. If the first layer is 0, then actually the result is not that N2 lives in H2, but that it lives in H2 modulo this particular subgroup, gamma 2. This particular subgroup is the subgroup that's generated by the 2 cocycle omega 2. Remember, omega 2 is the thing that specifies GF from GB. So let's define a map that sends something in this class to something in this class modulo this gamma 2. Sorry, there's a mess up with subscript here and superscript there. It should all be superscript. So from anomaly inflow, we expect that N2 should be Q gamma 2 of O2. So how can we see this gamma 2 structure from just the supermodular category itself? And the answer is that to get this O2 obstruction, we started with a supermodular category C with symmetry fractionalization on it. And then we picked a minimal modular extension, C check nu, and we tried to lift rho to rho check. But in principle, there could have been multiple distinct choices of nu that we could have picked. So I really should have put a superscript nu, which indicated this dependence, O2 nu. So now you can ask, how does O2 depend on nu? And it turns out that you can show that if you change nu, that O2 actually changes by this element of the kernel, alpha psi, that I had defined a few slides ago, raised to the difference in the nus multiplied by this omega 2. And this omega 2 was exactly the thing that generates this gamma 2 that we need to mod out by. So indeed, if we look at this Q, if we map this O2 onto that particular, onto this H2 mod gamma, Q, remember, was this map from H2 to H2 mod gamma. And if we look at Q of O2, then this equation will tell us that it's going to be independent of nu. And that's some other line here, but I guess I don't. So that's the point, is that's where this gamma 2 structure comes from. It's from this possible dependence on the minimal modular extension here. And it's only after you use this map Q that you get rid of that dependence. Okay, so there's various interesting consequences of this O2 obstruction. One consequence is if you look at the action of the symmetry on a torus, the ARF invariant shows up because of this O2. So I'm out of time, so I won't go through that. There's a nice picture for understanding why this O2 is related to anomaly inflow when you have this non-trivial N2 data. So then there's like the two more layers of this anomaly cascade. There's layer 3 and layer 4, but I'll just skip that. So let me just summarize the story then. But I hope I've convinced you that fermionic story is like significantly richer than the bosonic story, and it's quite relevant physically. So the key points were that we have to work with a supermodular category. We have aught LR versus aught. We have these bosonic and fermionic obstructions. There's a whole classification of fermionic symmetry fractionalization. then there's this cascade of anomalies that appear, which you can calculate. And now there is an interesting open question still, which is basically that I actually have all this data, and the data has to satisfy consistency conditions. So what we've done so far is we've derived the kth layer obstruction, assuming the k-1th layer obstruction vanishes. But there should be a bigger story here, that I should be able to derive this whole set of equations entirely from the supermodular category and trying to get an extension. And we haven't yet succeeded in doing that. And so you should be able to reproduce this entire Bordism group. I think that'd be really cool if we could see exactly how to do that, but we haven't fully done that because we haven't been able to derive this whole set of equations and then also see how they behave under stacking, which is like group multiplication in this Bordism group. So I think those are kind of open questions still left. So thank you very much.
Thanks very much for the lovely talk. Questions? Quite a few during the discussion.
Would GB be any group?
Yeah, any group. I mean, usually it's cleaner to work with finite groups, but I don't think we assumed anything actually. There's always a question when if GB is continuous, what kind of topology you assume, and this data continuous or piecewise continuous or whatever. So there are those questions. So I think basically that amounts to this structure appears, but if GB is continuous, it's not clear like exactly what cohomology we're talking about here. So, but there should be some cohomology because we can derive all the cocycle equations, coboundary equations, and so on. It's just a question of what continuity requirements you put on the data.
So are there examples in the Bordism group that cannot be reproduced by the Fermionic order?
No, but I can tell you that there is an interesting question, which is we don't have any examples of this H2 obstruction if GB is unitary. So I don't know what that means, whether it actually always vanishes when GB is unitary. Because all our examples are when GB is anti-unitary. That's my comment I can make about that.
So your answer to the first question caused me to wonder why you think that conjecture you stated is true.
Which I just stated many conjectures.
1.1 or something.
Okay.
And in particular, if you think it's true for like an arbitrary group, then what about products of the GB? Like how would that interact with the choices of new? Does that make sense?
Let me bring up the conjecture. So you're talking about this one.
Yeah.
Okay, and you're asking if GB is continuous?
So, so suppose that conjecture is true for one GB, and that specifies two news. And suppose the conjecture is true for another GB, maybe specifying two other news. What about the product of those GBs? Or something like that.
So actually, if GB is unitary, the news actually have to be the same. So that was kind of this theorem, although it's actually trivial. Yeah.
I could remark this last question that you mentioned about putting us in some more
This one?
on your summary slide, you said that it would be nice to
Yeah.
use this. I feel that this proof by Johnson, Fried, and Reiter of the minimal modular extension, the existence of minimal modular extension, it sort of used this kind of obstruction theory that I was alluding to, and I have to guess that within that paper would be the sort of these obstructions that you're list obstructions theory, and I would guess that the ingredients are probably in there. I'm not saying that claim is proved, but the place to look, I think, would be in the paper.
Yeah, I'm not familiar with it well enough. I mean, one thing is I think they only parity symmetry and not a generic GF. Like parity symmetry, you'd never have any of these obstructions. So
that'll change the computations, but the
yeah, maybe the overall framework.
The general framework should be there, I think.
I may make a comment. I don't think that's a statement about category theory. So exactly what the target is has no bearing on it. It's a statement in homotopy theory and just says when you're computing the homotopy groups of a mapping space, you start with the cochains on the source of coefficients of the homotopy group of the target, the computation of the k invariance of the target.
Yeah, that's what
homotopy theory statement. So
that's what
that's right. The target category is not important. That's just uniformly true. So in other words, that statement doesn't actually say very much by itself. It only starts saying something when you bring in the k invariants and computing them. So
I think there's also a question of like abstractly proving that this is an obstruction, and also just seeing whether algebraically you can see these.
we didn't define what that is, but it has to be the case. So when the group acts on a higher category, it gives a homomorphism with the automorphism of that category, and that's a question of homotopy theory, and that applies with a correct. If it doesn't apply, and it's a mistake in the definition of the group action of the category, or a mistake in the computation of the k invariance, or there's a mistake somewhere. This is a uniform general statement that has to hold here.
Constantine's just reiterating my comment, but with more confidence.
Well, no, I mean, it's not really a question that you should be able to get this. I would just like to understand how these equations come up, like when I work with the category.
So this obstruction theory that Constantine's referring
You're
to.
saying that like kind of.
There's first of all a general theorem, but it is somehow constructive. Like you can. There's the original paper that I think of as the ENO paper, homotopy theory and fusion categories, and sort of from the general chain, you get this what you call the cascade of anomalies by, you have some cell, you map the one cell in, there's some obstruction to mapping the two cell, you solve that, there's an obstruction. So there's it reproduces this kind of cascade.
Yeah, okay.
They're very hard to compute, by the way. I'm not saying it's
Well, yeah, I mean, I think the thing here is like we want to actually calculate these, and so that's the technology we're developing is just allowing us to do that. But yeah, I see what you're saying.
Any more questions for the speaker? If not, before we thank him again, let's resume at 20 after. So in 10 minutes, there's a coffee break now, and thank you again.